So let us take analysis of equal length orthogonal plane frames by Kanis method. Already we have done a problem with unequal length. Now we will take up equal length orthogonal plane frame having same height. So we will take up this example. So let us take this frame. This frame is definitely not symmetric even if I don't have this row. So it cannot be considered as symmetric because here one column I have taken 2EA, another EA. Otherwise this also would have been EA and this load was not there, means then it was perfectly symmetric. You could have adopted the other the procedure whatever I have just now completed. Now let us take this particular frame. As usual, first step, so we have to find out the moments at the ends of the members, and that we have to choose as the unknowns during our analysis. So these are the unknown moments. MAB, that is static independency. In other words, MAB, MBA, MBC, MCD and MCD, MDC. These are the unknown internal forces which we have to determine during our analysis by this Kanis method, that is static indeterminacy. And let us find out the kinematic indeterminacy of this particular frame. Of course, kinematic indeterminacy, as I told you, since it is a plane frame, there will be 3 possible displacement at each joint. So 2 translation and 1 rotation at each of these joints. At fixed joint, no displacement is possible. All the 3 displacements are 0 at these fixed joints. And we assume all members to be axially rigid. That's also one of the basic assumptions we are making in all the examples. And here, the vertical displacement at these 2 joints, they are 0 because these columns, they are fixed at the base. So we are assuming the members to be axially rigid, and this is fixed at the base. This end, though it is possible to move up or down because of this end being fixed, and this is axially rigid, this displacement is not possible. So this is also not possible. And of course, rotation at these 2 joints, B and C, that is theta B, theta C, they are possible. And translation, here suppose I will call the translation as delta, then this BC, and we assume axially rigid. So this end, if it moves either towards right or left, this also should move by same amount, and that is also delta. So unknown displacements are just theta B, theta C and delta. Since there is a translation in the structure, this is called as a sway type of frame. So that is what the conclusion we are making. Given frame is sway, and it is not on account of the load, horizontal load. If it is sway, it is sway, it is not. Even if it is not there, it is a sway frame. So that type of this thing notion in the mind, whatever you have, conclusion you don't have. Only you have to do this exercise and arrive at that. Unless it is fixed, this axially case, this end, if it is fixed, or by a roller or hinged joint, if this is held, then you can conclude it is not sway. That type of problem also we have done. Now it is a sway type of frame. Second, the next step, so we know the moment at the end of any member, because since we have to determine the moments at each of these ends of the member, you give the general formula, whatever you know, that moment at any end of the member is given by moment due to fixity plus twice moment due to rotation plus at the near end and moment due to rotation at the further end and moment due to sway. So this is the basic formula we have. These two are rotation contributions at near end and far end of the member. This is due to sway of the member together. This is without allowing any displacements. And this rotation contribution, it is given by rotation factor into sum of the fixed line moment of all the members making at the joint plus sum of the rotation contributions at further ends of all the members at the joint J, then sum of sway contribution of all the members meeting at the joint. So this is the formula for finding either MJK or MKJ. And the sway formula is MKK sway is given by displacement factor into sway moment plus sum of the rotation contribution of all the members at near end and far end rotation contributions that you have to take. And of course, I have given a factor C earlier for unequal leg. That factor you need not take because we are dealing with equal leg frame. That factor C will be 1. That factor C I have defined as story height by the height of the column. If the story height consists of different columns, the story, then which height you have to take? That because of that, you have to assume one height of the column as the fixed story height, and that factor you have to determine and that you have to apply. So this we have. Then next second step, you have to find out all the quantities to use this formula. That is, all the quantities for fixed line moment that you can determine. Here we have MAB, BA bar 0, CD and DC bar 0 because no member load, only we have on the member CD. There is a load, due to that load we have fixed line moment that is minus 150. Then third step, and of course you can say here MAB bar equals MBA bar equals MCD bar, MDC bar. They are all 0 because there is no member loading, only on that. Then third step, you have to find out rotation factor, which is nothing but minus half into K by sigma K. So this rotation factor is 0 at ends, fixed ends, because at fixed end there is no rotation. So naturally the rotation factor is 0. That is at A and B they are 0 because they are fixed. Only at the other ends, B and C, that's other joints, we have to find the rotation factor, that is joint B and C, we have to find this rotation factor. So you write all the members at each of those joints. At B we have BA, BC, at C we have CB and CD. At EA, I is 2, and then find the stiffness K, which is I by L, relative stiffness I will determine, which is I by L, 2I by 6, it is I by 3. Then BC also 2I by 6, I by 3. CD is same as BC, I by 3. CD is I by 6. So then sigma K, which is 2I by 3 here. Here it is I by 2. 6 is here. 2 plus 1, 3. 3 by 6 is half. Okay. Then RF you can find out, which is K by sigma K into minus half. So it is here half into minus half, minus 1 by 4, minus 1 by 4. Here it is 2 by 3. 2 by 3 into minus half, that is minus 1 by 3. Here it is 1 by 3 into minus half, that is minus 1 by 6. You can make the check. Check is that each joint, sum of the rotation factor at each joint should be minus half. It is minus half here. Here minus 1 by 3, minus 1 by 6. That's also minus half. So whatever calculation you have done, it is okay. Next you have to find displacement factor, that is fourth step, that is extra from previous example, because we have to determine displacement factor. This is done, these fixed end moments, they are all known. Here M or displacement factor, it has determined. So already I have told this how to find out. You prepare a table, write story number. So here it is only one story frame. Earlier we had 2 stories. You can take that number of stories, 1, 2, 3 like that. So then you can say story height. Here it is story height HR. It is constant. It is
6 meters.
6 meters. HR you can say straight away 6 meters. Then story shear. Story shear QR, that is I defined as all the horizontal forces, sum of all horizontal forces acting around the story. Here is it only one story, sum of horizontal forces, just
20.
one load, 20 tons, 20 kilonewtons, that is acting in the opposite direction than the global positive direction. So it is minus, so we have to take it as minus 20 kilonewtons. Then story moment, that is MR, which is QR HR by 3. HR is constant, so QR minus 20 into 6 by 3, it is minus 40 kilonewton meter. So that's all the steps. Then you have to find story columns. So in this story, you have 2 columns, AB and CD, because only columns will undergo sway. Here you have seen in the first step, only this column AB, CD will undergo sway. Beam is not undergoing any sway, so that you need not take story columns only, we are writing, that's why. Only columns. Story columns A, B, C, D, K value of that A, B and C, D, it is I by 3. Here also I by 6 here. So then that C factor we need not have to bother. Forget it. Only sum of the stiffnesses, that is I by 2. So then find out displacement factor, which is nothing but minus 3 by 2 K by sigma K. Earlier we had Ck by sigma Ck. Because of that unequal leg, now it is equal leg, so you can, things are simplified and steps are a little bit reduced. So this is much more simpler when compared to unequal leg. Friends, find out this I by 3 minus I by 2 K by sigma K, which is nothing but 2 by 3. 2 by 3 into minus 3 by 2, it is minus 1. Then K by sigma K, I by 6 by I by 2, it is 1 by 3. 1 by 3 into minus 3 by 2, it is minus half. Here you can do the check. Check is sum of distribution displacement factor at each story should be minus 1.5, minus 3 by 2, that you are getting here. So here unequal leg, you are applying the C factor also. C into distribution factor. C into this, C into this, you are taking. Now that thing is not there. So these are the preliminary calculation you have to make, and you can go for Kanis moment distribution. That is fifth step. Let us perform Kanis moment distribution and arrive at the rotation factor and sway factor. Sway moment, this thing due to rotation and sway contribution. Let us find out by trial and error. So as usual, I will write this is fifth step. One is moment distribution. So I will write only the joints B, C, that continuous joints. So with two rectangle or square blocks, one inscribed the other like that, and the fixed ends, I will write it as it is. So this is A, this is B, this is B, this is C, and the columns A, B, C. Here I will write that column story movement, because there is only one story. I will write in the left corner
minus 40
of that story, that is minus
40.
40. That you should not forget. That I will transfer first. Story moment I have transferred. Then I will transfer these things one by one. Fixed end moment, only on BC you have minus 150, CB we have plus 150, the rest are all 0. I have transferred that. Here I will find out sum of the moment, fixed end moment at each joint. I will write that a joint B and C, sum of the fixed end moment. Then rotation factors I will write a joint B I have for BA, that is this is BA minus 1 by 4 and BC minus 1 by 4. A joint C, CB it is minus 1 by 3, CD it is minus 1 by 6. I have transferred all the rotation factor also into that diagram. So that's done. Then straight displacement factor, that is for the columns A, B and CD. I will write it at the center of the columns. So that is for AB, it is minus 1. For CD, it is minus half. If that C is equal to 1 column factor, because it is equivalent, that also you have to write it if it is unequivalent. So all the values which I have determined earlier steps 1 to 4 I have transferred onto the. Now I will concentrate on only the Kanis moment distribution in this diagram, cycle by cycle, until the convergence occurs, or the rotation contributions at each of those member ends as well as straight contributions. Then I will use that formula for finding the final moment. So I will start as a rough scale. I will take cycle 1. I will apply the second formula. I will start from the left hand corner joint, that is joint B. I will start. Then I will move in the horizontal direction, joint by joint. Then next story, like that I will move. First you start with joint B. So in that formula, first thing is rotation factor. I will leave it. First I will determine the rotation contributions at each of the joints. A joint B rotation contribution other than that RF, I have to find sum of the fixed end moment. MKZ bar, that is minus 150 plus rotation contribution at the further ends. That is sigma MKZ. Here it is 0, here also it is 0. Anyway, nothing is coming here. So it is plus 0, that sum, which is nothing but minus 150. This sum I have to multiply by the rotation factor RF. So that minus 150 into minus 1 by 4, that is 37.5. Here also 37.5. So in the joint rotation contribution for BC and BA. Next I will go to the joint C. So here sum of the fixed end moment, MKK bar, that is 150 plus contribution MKJ bar sigma 37.5, which is 187.5. Then that sum I have to multiply by the corresponding rotation factor, that is
minus 62.5. 62.5.
8 minus 62 point, and not this.
Minus 31.25.
3
minus 31.25.
minus
31.25.
31.253. I am only talking units. Strictly speaking, you have to go up to 4th decimal. Then only you will get perfect convergence. So next, B and C over joint A and D. So they are fixed, no contribution due to rotation. Forget it. So this is cycle 1. over of rotation contribution. Now since it is a sway plate, I have to find out these sway contributions. Now that sway contribution, I have to use that other formula, that sway contribution MJKS is equal to, so MR, displacement factor, that I will come to that afterwards. Only that sum I will determine, that is MR. MR is minus 40 plus sigma MJK or rotation contributions, that is 37.5, here it is 0 for this column. Here it is minus 31.3 plus 0. So it is just 37.5 minus 31.3, that's all. So that sum I have to multiply by the corresponding displacement factor. So this is 71.3 minus plus 37.5, it comes to 33.8, just check.
Yes, sir.
Okay,
33.8.
33.8, that sum into
Minus
this
1.
huh?
Minus 1.
Into minus 1, that is 33.8. That I will write it in this fashion and write it the other way because it is column sway moment factors. So this is 33.8. This is exactly half of that value, 16.9. So the cycle 1 is over. Next go to cycle 2. Cycle 2 on same lines, B, repeat it, minus 150 plus A contribution minus
62.8.
Here it is 0. It is just
Minus 212.8.
minus 212.8. That into minus 1 by
Minus
4.
1 by 4. 53.2.
53.2. 53.2. I can cancel this. So next joint C, it is 150 plus
53.2.
653.2 is equal to
203.2.
203.2. That multiplied by minus 1 by 3, 67.4.
Yes, sir.
Then here it is 203.2 minus 1 by 6.
Yes, 1 by 6. Minus 33.8.
33.8. So this is that rotation contribution at B and C. At A and D again it is 0. Let's go to sway contributions. So that is again first sway moment MR, that is minus 40 plus
53.2.
rotation contribution at the ends of all the column members in that, that is 53.2 plus 0 minus 33.8 plus 0, that is 53.2 minus 33.8.
Minus
Oh,
20.
here I forgot to take that.
No, sir, taken, sir, taken.
Okay, this is sum is
Minus 20.
73.8 minus plus
Minus 20.6.
that is equal to
Minus 20.6.
minus 20.6. That multiplied by minus 1.
20.6.
20.6. Half of that value is this
10.3.
10.3. This is cycle 2. Then lastly I will do one more cycle and stop with one. Cycle 3. Again same thing. I'll just move fast. Minus 150 plus
Minus
minus 67.4.
Minus
That
217.4.
is equal to
Minus
217.4. That divided by minus 1 by 4.
54.3.
54.4.
54.4.
54.4. Then next joint is joint B. Next joint
50.
C. It is 150
Plus
plus 54.4.
204.4.
Oh, sorry, this way contribution I didn't take.
Yes, sir, taken, sir. It's
Yeah.
over, sir. Minus 40.
Anyway, it doesn't matter. I told you, any mistake committed in any one cycle, that get automatically rectified. 54.4. Then here rotation contribution
Yes,
0. Then sway contribution.
Sway contribution.
10.3. That sway contribution at B I did take.
Yes, sir. Yes, sir.
So here 150
minus
minus
150
67.4, sway contribution of 20.6. I should have taken. So this is the value.
in cycle 2 also we have to take.
No, not this. Here. Correct, no?
Yes, sir.
Here it is 20.6. Previous also have not
Previous also
taken.
they have not.
Anyway, from cycle 3 onwards, you can just take that. This particular sum, it comes to 217.4 plus 20.6. It comes to
230.
196.8 minus that divided by 1 by that divided by 4 minus 4, you will get
Minus into 1 by 4. 49.2.
49.2. So that's okay. Here also 49.2. Next, here it is 150 plus 49.2 you have to take. That is rotation contribution. Then sway contribution 10.3. That is equal to
209.5.
209.5. You divide it by minus 3, you will get minus
69.8.
69.8.
8.
Then divide by minus 6.
34.9. Minus 34.9.
34.9. Next, sway contributions. Sway contribution, that is story moment plus sum of the rotation contributions at these ends. 49.2 minus 34.9.
Minus
40
plus 49.2 minus 34.9
34.9
equals.
So this is equal to some minus 74.9 plus 49.2, which is nothing but
minus 25.7.
25.
Minus 25.7.
Minus 25.7. That multiplied by minus 1, it is 25.7. Half of that value
12.9.
12.9. So I will stop this at this stage. You can continue further. I will indicate that last step, that is fifth step, final
Moments.
moment. Final moment. This is after 3 cycles I am getting this value. So it is not fully converged. Anyway, it doesn't matter what steps are required. I will find out MAB, which is equal to MAB bar 0, then times the rotation contribution, that is 0, plus contribution at the further end 49.2, then sway contribution 25.7. So this will be equal to
74.9
kilonewton meter. This is MAB, then MBA is equal to this 0 fixed end moment twice rotation contribution twice into 49.2, that is 98.4 plus rotation contribution at the further end 0, sway contribution 25.7, which is nothing but 124.1 kilonewton meter. Then find MBC, that is fixed end moment,
minus 150.
minus 150 plus twice rotation contribution 2 into 49.2, that is 98.4, and contribution from the further end 69.8 plus sway contribution. BC has not undergone any sway, so that is 0. So this sum is equal to
minus 120.
minus 219.8 plus 98.4.
Minus 121.
121.4. So minus. So this actually check is MBA plus MBC has to be 0. I am getting this error because I am closing at a lower cycle. So that is acceptable. I will leave it. Then MCD on same lines. That also I will check MCD, and then we can plot the bending moment diagram. MCD is fixed end moment twice rotation contribution, that is 139.6 twice 69.8 plus contribution from the further end, that is 49.8 to then sway. This is not undergoing any sway, it is 0. So this value will be
59.6.
59.2 minus 139.6.
59.6.
59.6. And last MCD. MCD is fixed end moment 0 twice rotation contribution 2 into 34.9, that is 69.8 plus rotation contribution at the further end, then sway contribution. Here we got 12.9
minus 56.9.
that is equal to
minus 56.9.
minus
56.9.
56.
56.
56.9. Here also the sum MCD has to be 0. I am getting this small error of 3 point something. That is because I am rounding it over 3 cycle, and one step we have committed some mistake of not taking that sway contribution. That if it is not there, I would have got that of the 3 cycle itself. Then lastly, MDC is no fixed end moment. Twice rotation contribution 0, further end contribution minus 34.9, then sway contribution 12.9. This is equal to
minus 22.
22 minus. So these are the fixed end moments you got. Then finally you can plot the bending moment diagram. So this is like this. MAB 74.9 clockwise, MBA 124.9. I will take somewhere 124, and here also
124.
121, and here
59.6.
clockwise, here it is 59.6. Then here it is
minus
MCD minus like this 59.6 it has to be. Then here it is 22 minus. And you can plot. First you plot this fixed end moment on the tension side, that is on the tight side of this arrow, that is 74.9. Here it is 124. Like this. This is 74.9, 124. Here also it has to be 124. That is slight error is there. And here 59.6. So that you can take it. Here also 59.6. Here you got 22. And superposed free movement diagram. That's WL squared by L. That is 224. So this is negative, positive, negative, positive, negative, positive. So this is your bending moment diagram due to is about equal leg sway friend. So with this Kanis method, complete all varieties of problem, about 7 problems we have worked. So all varieties we have done. Next we will take up matrix stiffness method.